In this segment about phase changes, we're also going to be simultaneously completing a worksheet. And if you can find that worksheet, it's called a heating curve. It's printed front and back. And as I go through the PowerPoint, you'll be able to answer many of the questions that are on that worksheet. And we'll pause if appropriate for you to have time to do so. I did want to point out that each of the questions on the worksheet have to do with different parts of that graph. And if you are not able to answer the questions about what is happening to the energy in this segment, then wait until the end of this podcast and you'll see a good summation of that. So let's go on. Of course, we haven't completed the heating curve worksheet. We're getting ready to do so. But when we do a phase change, we're just changing the matter in one state into another state. And so now you can see a rough approximation on this graph of what's on your worksheet. On the horizontal axis, what we're looking at is time going by, but what's really happening here and what is not shown is heat is being added. On the vertical axis, what you're seeing is a change in temperature, but I want you to write by both of these things a clarification. By time, I want you to put heat being added. By the word temperature, I'd like you to write kinetic energy. Because really, what temperature is measuring is changes in kinetic energy. And we're going to connect this to how do changes in kinetic energy impact the forces, the intermolecular forces, not bonds, that holds matter together. Hopefully you've made that change. Heat being added, kinetic energy on the vertical axis. Now in the first segment on your graph, you are at minus 10 degrees Celsius. And if we're talking about water, then that means your water would be completely existing as solid ice. And as time goes by and you add more and more heat to that solid ice, up to, but not including 0 degrees Celsius, you're going to see the temperature warm up. The kinetic energy is going to be increasing a little bit, but it's still going to be ice. And it's not until you've added enough heat over enough amount of time, and on this graph it looks like it's about approximately, 5 minutes, that you will begin to see your solid form of water turn into the liquid form. We are now at segment B. And on segment B, you can see that there are two phases of matter present. We have liquid water and we have solid ice. And what's interesting about this is that the graph has gone flat. And if in your math class you remember when graphs go flat, no change is occurring. Well, clearly a physical change is taking place. Solid is melting into liquid, but the kinetic energy is flat. It's not changing because the line has gone flat. Temperature is a measure of kinetic energy. We know we're still adding heat, and what must be happening is that heat is being used to break those intermolecular forces that hold the solid as a solid and are now turning it into a liquid. You notice that this takes place at 0 degrees Celsius. 0 degrees Celsius then can be thought of as one of two things. For water, it's its melting point if you are adding heat to ice. But if you are removing heat from liquid water, 0 degrees Celsius is also known as the freezing point. So when you look at this thermometer, see how it says 0 degrees Celsius? The thing that's most important for you to get from this particular slide is that temperature will not change as long as there is some solid ice present. Assume we are warming up this beaker. As long as there are some solid ice cubes present, the temperature of the water will read 0 degrees Celsius. But when the last smidgen of solid ice melts away, then and only then will you begin to see the temperature rise. So during a phase change, in this case solid turning into liquid, temperature is constant, kinetic energy is constant. Now once you reach a particular point on this particular graph, at 20 minutes into the process, that last little bit of solid ice disappears, and now we have 100% liquid water. Look what happened to the slope of the curve again. It's rising. We're continuing over time to add heat. The kinetic energy starts to rise again. I'm still having my liquid water remain as liquid until sufficient heat has been added for it to change into the next phase. So during this rising part of the curve, there's only one form of matter, and that's liquid water. And clearly the kinetic energy must be increasing, so the molecules are moving around more, the temperature is continuing to rise, and at this point in time, there's no phase change taking place, but there will be shortly. So at segment C, we're simply watching liquid water getting warmer. But eventually you reach a point, and that point is when segment D begins at approximately 80 minutes into the process. And you can notice that at this point in time, the temperature is 100 degrees Celsius, the line goes flat again, and I think you know what's happening here at the boiling water phase. The water starts to boil. And what's happening again is the line went flat, which means that kinetic energy is constant. But there must be some sort of changes in potential energy going on, which we'll describe in just a moment. But for the moment, what you've done now is you've reached a point where so much heat has been added that you're able to break the hydrogen bonds that are holding water together as a liquid, and now you're turning it into steam or a vapor. So again, the line goes flat when there is a phase change, a change of form of matter into another form. So 100 degrees significance is important because it shows us the temperature at which water boils when the pressure is 1 atmosphere. More on that later. But again, if you think about it going backwards, if you had boiling water, cooling it down, taking steam, at 100 degrees Celsius and cooling it down will turn it back into liquid water. So 100 degrees Celsius, yes, it's the boiling point for water, but it is also the condensation point for steam, the temperature at which it begins to turn back into a liquid if you were removing but not adding heat. So here's an example of a geyser, probably in Yellowstone, lovely place to go. And if you continued to heat that steam, which was present at segment E, not shown on this graph yet, we'll get there, it will get very superheated, and here is an example of a geothermal field where we harness the geothermal energy of the earth to turn turbines to generate electricity. Not so much steam in years of drought, unfortunately. So here is a picture then again of the graph that you were supposed to be working with, except now they've added this segment E, which is not shown on your particular worksheet. And it's not demarcated, but when you are at the flat point of the first segment there, that's where the graph goes flat, kinetic energy is constant. That could be considered to be the melting or freezing point. And here is the part that comes back to answering some of those questions about what is happening to the energy that's present in segment B. Well, potential energy, change is taking place. So even though kinetic energy is being constant, it must be that potential energy is being used to overcome the forces that are holding the ice crystals together. So the temperature will only begin to increase after all of those forces are overcome, after the last bit of solid ice melts away. So in this segment, it's potential energy that's being used to melt the ice. Kinetic energy is remaining constant since temperature doesn't change. Take a moment and make sure you jot that down. It looks like that's approximately question 2B. Now when you reach segment C, there's still changes in heat going on the whole time because as time goes by, the person is adding heat. You will see increases in kinetic energy, and the liquid molecules are getting farther away from each other as we continue to break those forces. So that's why the graph's temperature begins to rise. And I think that's referring to the question B on number 3. What is happening to the energy being absorbed? When you finally reach the boiling point of liquid water at 100 degrees Celsius, now we're back to line is flat, kinetic energy is constant, potential energy is being used to break the intermolecular forces that hold liquid water together. And sadly, they're called hydrogen bonds, even though they're not a bond, they're a force. So when you're answering question number 4B, what is happening to the energy being absorbed, then you are answering it by saying it's being used to break the hydrogen bonds, the intermolecular forces that hold the liquid water together. And it asks, what is the significance of that segment D? Well, that is the boiling point, yes, but it also is the condensation point for steam. So make sure you add that into your diagram. Boiling point and condensation point are at the same temperature. And it refers to, on question 5, what would you expect to happen if the heating was continued? Well, you'll have steam that's hotter than 100 degrees Celsius, and that's what we would call superheated steam. Okay, so this is a fairly primitive graph because it doesn't really show the correct numerical relationship between the heat it takes to melt ice and the heat it takes to vaporize. So on this next graph, as you wrap up any questions, you can see that there's going to be a different shape that will correctly refer to the heat of fusion. So I'll give you a moment to write that down. The heat of fusion is just a fancy word for the amount of energy needed to melt 1 mole of ice. And the length of that segment on B is what I was referring to. It should be different than the length of segment D, but I'll show you in just a second here. So it's the energy needed to melt 1 mole of ice, or 1 mole of any solid substance into its liquid phase. So D must be the heat of vaporization, the energy needed to boil 1 mole of water. Let's make sure we say that correctly. Heat of vaporization is the energy needed to vaporize 1 mole of any substance. In this particular case, it's the energy required to boil or vaporize 1 mole of water. And those take place at very familiar temperatures upon which we base the Celsius scale. So let's continue on and find the correct picture, though, for heat of fusion and heat of vaporization. And notice the symbology is interesting. The delta symbol here means change. H stands for heat, and fuse means to just melt. And the same would apply to the heat of vaporization symbol. We use VAP. You can also have a heat of sublimation, and we'll talk about sublimation in just a moment. It's the ability to transfer heat to a substance, but it goes directly from a solid into a gas. It does not have to melt first. And you've seen that if you've ever observed dry ice or solid CO2 seemingly to just disappear without having to melt first. That can only occur under certain conditions, and we'll explain that when we study phase diagrams. Okay, here's that better graph to which I was referring. The temperatures are a little bit different. The heat being added is more correctly shown instead of time going by. But I want to point out that the length of the segment that shows the amount of heat needed to melt 1 mole of ice is much shorter than the length of the segment for the heat required to vaporize 1 mole of liquid water. And there's a reason for that, which can be explained based upon intermolecular forces. And I'll show you a graphic here in just a moment that will clarify that. This is a better representation of the heating curve. So here is one slide that summarizes the 6 common phase changes of matter, assuming you're not turning something into a plasma. The red symbols show heat needing to be added. The blue font refers to when heat is being removed. So for example, to melt or freeze a liquid and solid back and forth into each other requires the same amount of heat to be either added if you're melting or removed if you're freezing. You are responsible for knowing the 6 phases of matter. I think most of you are familiar with the first 4, melting, freezing, vaporization, and condensation. But sublimation and deposition are the ones that are new to many of you. To sublime a solid, you add this much amount of heat to directly turn it from a solid to a gas. Notice it doesn't melt first. And deposition is when a gas turns directly into a solid by the removal of the same amount of heat. So here's just a rephrasing of the same phase changes with which I think you are familiar. So I'm not going to spend too much time on that slide there. But we do need to notice that when you are adding heat or removing heat, that's when you can have these changes in phase. So endothermic processes are when you heat a solid to melt it. You heat that liquid that forms it more and it will boil and become a gas. So those are endothermic. They require energy to be added. And that's represented by the large red line below. If you go the opposite direction, let me make sure I do that correctly, you have to chill or remove heat from steam to get it to condense, in this case 600 calories, and then you have to remove another 80 calories to get liquid water to freeze. So they're exactly the same amounts, they're just being either added or taken away. So back to that explanation then with this graph, which I like a lot. It shows a bar graph representing the amount of heat of vaporization and the heat of fusion for various substances. So the sort of purpley color small parts of the bar graphs at the bottom of each column represent the heat of fusion. And notice that the blue segments for each of these substances is much, much larger. That represents the heat of vaporization. And I want you to think for a moment about why it takes so much more heat to vaporize 1 mole of a substance than to just melt it. And it has to do with the form of matter. You just got done studying gases. Gases have large volumes that they take up if allowed, and they have very small forces of attraction between the molecules. They're very far apart from each other. So the reason why, for example, on water, it takes 41 kilojoules to turn liquid water into steam, but only 6 kilojoules per mole to melt a mole of ice, is because in melting, you only have to break down some of the intermolecular forces. When you vaporize, you have to completely destroy all of the intermolecular forces. And that's why heats of vaporization are always so much larger than heats of fusion. And that's why on the previous graph, the line showing water being vaporized was much longer than the line showing ice being melted. Okay, that's it. We'll talk about vapor pressure at the next time.